Hey everyone, welcome back to Statistics. And in today's session, we're going to actually look really close at how to perform a significance test for a proportion. Now, I'm not sure if we're going to go into an actual beginning to end proportion test, but we're going to have to look at very least, we're going to have to look at the basics of everything that you're going to have to do in order to make a significance test for a proportion. So let's go ahead and get started. And for lesson 9.1, we use a simulation to estimate the p-value to decide whether or not Mr. Ferreira was exaggerating about his free throw percentage. And today we're going to use a formula to find a p-value. And yeah, I don't remember that either, but I guess in a past iteration or in a past life this happened. So we're going to carry out a significance test, and before we do that, we have to write a hypothesis. And our hint is that we're trying to prove that Mr. Ferreira shoots less than 80% free throw. I had mentioned earlier that if you are going to use a statistical variable like p, you're going to have to define it first. So we're going to say p is Mr. Ferreira's true free throw percentage. We get that hint there of 80%, and that's all we need to really write our null hypothesis. But for the alternative hypothesis, we're going to have to do a little bit more digging. And what do we want to prove? Same hint says we want to prove that Ferreira shoots less than 80%. So I think that should be my alternative, less than 80%. Okay, so each class found a different p-value because the dot plots were different. You'll remember that this was when we actually did the simulation. So would it be appropriate to use a normal distribution to sample p hat? And this question is something that comes preloaded with a way to answer that. Normal distribution, sampling distribution for p hat. That should automatically bring your head around to large counts. So let's check large counts. From the experiment, we had n was 50, and from our null hypothesis, p is 0.8. Okay, that's equal to 40, which is definitely greater than 10. So now we got to check the other one, n multiplied by 1 minus p. So 50 times 1 minus p, so 50 times 0.2 is 10, and that is also greater than equal to 10. Remember, I usually don't just multiply that. I just find out, well, we need to get from 40 to 50, 40 being NP and 50 being the sample size, and that's where I get that 10. If you want to kick your understanding up a bit here, you can say that since NP is greater than equal to 10, and n1 minus p is also greater than equal to 10, we can use a normal distribution. Are there any other conditions we should check? And yeah, these conditions came in sets of 3. There was a random condition, so we should check that. And we should also check that 10% condition. Random sample, again, it does 2 things for us. The first thing that it does is that it ensures that we are taking an unbiased sample. So our sampling distribution is centered upon the population characteristic or parameter. And the second thing it does is it allows us to generalize our findings to the entire population. Now for sample size, remember we do that because we are sampling without replacement. So that in essence changes our formula for standard deviation. So we need to make sure that our sample size is small enough where that change in the standard deviation itself won't be very big, or at least not big enough to matter. Now, as far as meeting those conditions, did we have a random sample of free throws? You can kind of argue it both ways. I mean, I'm sitting there shooting free throws, but if it was a random sample, then you really would have taken free throws from a bunch of different days and put them together into a sample. So I could see both. As far as 10% of the population, well, I've definitely shot more than 500 free throws in my lifetime. So yeah, I would say that is we satisfy the 10% condition for that one. Well, now that those conditions have been met, let's find the mean and standard deviation for the sampling distribution of p hat. Okay, mu of the sampling distribution for p hat is the same thing as p. Now this number is always going to come from the null hypothesis. Now that is a necessary feature of a hypothesis test, is that we have to assume that the null hypothesis is true. And the null hypothesis says p equals 0.8. So that's what's also going to be the center of the sampling distribution for p hat. Now the standard deviation of the sampling distribution, we have a formula for that too. That is p1 minus p over n. And just like with mu p hat, our p here is still going to be 0.8 because we're defining it to be true from the null hypothesis. That gives us a value for sigma p hat of 0.565. Next, it says here to use the mean and standard deviation to label a normal curve. And I don't think I like this normal curve all that much. So I'm going to put my normal curve. Okay, that's a nice looking normal curve. And let's see, 0.8 is going to go right in the middle there. And then we're just going to add 0.565 and subtract 565. Okay, I think I did that pretty well. 0.8 for the mean, right in the middle. Minus 0.565, and I went and did it to 3 decimal places just so we're going to fit a little bit better here. But here is our normal curve, which is kind of foolish of me in hindsight or in foresight. I don't know, because I needed to go all the way down to 0.64, which means I needed to go all the way to 3 standard deviations. Okay, so we're supposed to label 0.464 on the map, and that's going to be somewhere between -3 and -2 standard deviations. Let's zoom in there. This right here gives you a little bit of an idea about where 0.64 lies in the normal curve. Scrolling up to our alternative hypothesis over here is less than. So when we compute area, we need to go less than my test statistic, meaning that this red area over here that I've gone ahead and colored in, that's going to be my p-value. And that's very small. If I remember correctly, the area to the left of a z-score of -2 was was 0.025. So that area is less than 0.025, meaning our p-value is less than 0.025, which is less than 5%. That's statistically significant. Okay, let's back up. We really want to find out the z-score for 0.64. So let's get our z-score equation. What we're going to see is that z is going to be equal to p hat minus mu of p hat over sigma of p hat. And it's a good thing we have numbers for all of those. We've got a p hat of 0.64, mu p hat was 0.8, sigma p hat was 0.0565, and this will give us a z-score, and I'm hoping it's somewhere between -2 and -3. Yeah, that z-score is going to be -2.832. And in the context of a hypothesis test, we call that number the test statistic. Okay, so let's back up and we'll get to our important ideas here. We've got, totally my mistake, we have more to do, my bad. Find the probability that an 80% free throw shooter will make 32 of 50, p hat being 0.64 or less. So remember what this is saying, or think about what this is saying. We are starting with the assumption that I shoot at 80%. And then if I do shoot at 80%, what's the probability that I would have only made 32 out of 50 or less than 32 out of 50? Now in statistics and probability notation, we would say this is the probability that a z-score is less than negative 2.832. On your calculator, you would write norm CDF, low of 0, high of 0.64, because we can't have negative percentages. And then mu is 0.8 and sigma is 0.0565. Both of those calculations give you a p of 0.0032. And you know that normal calculation that we just made? We just calculated a p-value. So a p-value really is just the same thing as a normal calculation. There's no difference between the two. A p-value is where on the sampling distribution a test statistic lines up, and what is the z-score associated with that, and what is the area associated with that z-score. See how everything has just come together, all those normal calculations we did, everything that we did about sampling distributions, everything we did about experimental design, all comes together in this one problem, and it comes to give us a number like 0.0032, which is quite small. But that's what we want, because small means statistically significant. For the conclusion, you're just going to grab and copy and paste a conclusion for a hypothesis test. So since the p-value is, and it's small, so less than, now nowhere in this problem was an alpha stated, so we're just going to have to use a standard alpha of 0.05, and since it's not written anywhere, we better at least write it in the conclusion. So we have a small p-value, so it supports the the alternative hypothesis. And alternative hypothesis in context. Read it one more time for readability. Since the p-value is less than alpha, the data supports that Ferreria shoots less than 80% free throw percentage. That sounds pretty good to me. And that takes us through all of the steps that we need to do for a hypothesis test for a proportion. So let's get ourselves down to our significance test. Important ideas. Now the first important idea has to do with the conditions of the significance test. And if you studied last chapter, then this is really easy for you, because these are the exact same conditions that we used for a confidence interval for p. So you needed a random sample or random assignment. The 10% condition has to be true. In other words, the sample size has to be less than 10% of the population. And then the large counts has to be true, where NP is greater than or equal to 10 and N1 minus P is greater than 10. Now for the test statistic and the p-value, we talked about those as we were just working. And you want to go ahead and make yourself a normal curve and label it with mu p hat and sigma p hat. Mu p hat is p, and sigma p hat is root p 1 minus p over n. Those values of p, or the value of p, comes from the null hypothesis. And you know, the mu p hat and sigma p hat, again, that comes right out of the sampling distribution and right out of the confidence interval. The test statistic is p hat minus p over root p 1 minus p over n. Just rearranging a couple things over here, and I'm going to zoom in. And we have the test stat is always going to be equal to the statistic minus a parameter over the standard error. And that's going to be equal in our case to be p hat minus mu p hat over sigma p hat. And some of you might prefer to see everything substituted in there. So that's p hat minus p over root 1 minus p over n. So it doesn't matter which of those two formulas that you use, they are identical through equality. And then finally, we have the idea of the p-value, and the p-value is just a probability on a z curve that z is either greater than or less than the test statistic. So that's quite a mess of formulas, but you've met most of those before. So, this is where it pays to have been really, really diligent the last couple of chapters. Let's go to check your understanding. According to the U.S. Census Bureau, the proportion of students in a high school who have a part-time job is 0.25. An administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than the national figure. So she would like to carry out a test at the alpha equals 0.05 significance level, and the administration selects a random sample of 200 students from the school and finds 39 have a part-time job. Typical kind of question, I should say. Part A. State the appropriate hypotheses for performing the significance test. Be sure to define the parameter of interest. So right away, P is a proportion of high school students with a part-time job. H naught is P equals 0.25 and HA is P is less than 0.25. Remember that the administrator suspects that the proportion of students at her high school who has a part-time job is less than the national figure. And that's why we have less than 0.25. Let's explain why there is evidence for the alternative hypothesis. And what did our sample tell us? Evidence comes from the sample. So the sample is 39 out of 200. P hat then is 0.195, and that 0.195 is less than the null hypothesis value, the test value, or the hypothesis value of 0.25. And that's our evidence. Now, if this P hat happened to be greater than 0.25, which means it's going opposite of our alternative hypothesis, then we shouldn't even bother doing this hypothesis test. You're going to get results that are not statistically significant. Let's check the conditions for performing a significance test. For the random condition, we are told that this is a random sample, and I always like to put that in quotes, quote something directly from the problem, so we can satisfy this. For the 10% condition, we have to see that our sample is less than 10% of the population. So the sample is 200 students. 10 times 200 is 2,000. So there has to be more than 2,000 students at this school in order for this to pass the 10% condition. So we would write something like, there needs to be more than 2,000 students at the school so that n is less than 10% of the population. And this does seem likely. Most schools that I come in contact to, I don't know about you out there, but definitely at my school, we have more than 2,000 students. So 10% condition sounds good. For the normal condition, since we're dealing with proportions, we need to go to large counts. Okay, NP is equal to 39, which happens to be greater than or equal to 10. And try not to bog yourself too much with these calculations. NP is just a number of successes. And we were told that 39 students had a part-time job. So NP is definitely greater than or equal to 10. For N1 minus P, again, don't bog yourself down too much with calculations. If there were 39 successes from the sample, that means there were 161 failures from the sample. Or, failure is a harsh word, but you know what we mean in this context. 161 students did not have part-time jobs because 39 plus 161 is equal to the sample size of 200. In any case, that number is greater than 10. So having passed large counts, we are okay to proceed with our test. So to make things super fast, you can just go right to the test statistic right now, because presumably you understand that you are looking at a normal curve. So let's get our test statistic calculation. So for any test we do, the test statistic is going to be the statistic minus a parameter over the standard error. The next thing you're going to do is get the specific formula for that. Okay, p hat minus p over square root of p1 minus p over n Then you're going to substitute numbers. After you substitute your numbers, you're going to go to your calculator and calculate. I'm getting myself a test statistic of negative 1.796. It's always a good idea to draw a normal curve. So we'll get our normal curve. You can go ahead and shade in the region, and I think we need to do less than. Remember, our alternative hypothesis would be less than. So our shading is less than our red line. We have the test statistic, negative 1.796 up here, and down over here we have our p hat, 0.195. And lastly, we should write down our p-value. It's going to be the probability that z is less than negative 1.796. On your calculator, it would be the normal CDF, low of 0, high of 0.195, mu of 0.25, and sigma of 0.0306. And I got myself a p-value of 0.0361. Let's remember that we were testing this at the alpha level of 0.05. So 0.05 is definitely greater than our p-value, or maybe we should say our p-value, 0.03, is less than our sigma, our alpha level, 0.05. So we should reject the null hypothesis, or we should support the alternative hypothesis. Go ahead and copy and paste the sentence frame. Read it one more time for readability. Since the p-value is less than alpha, the data supports that the proportion of high school students with a part-time job is less than 0.25, and that reads pretty well to me. That is a job well done. Okay, guys, and that kind of takes care of our first look at the hypothesis test for proportion. Hopefully all of these things are really coming together for you, and if they're not, you'll need a little bit of practice. It always takes just a little bit of practice to get this stuff done. So, that said, I'll see you guys later for the next one, when we really formalize this process with another 4-step plan.